Hey math fans, Alex here, coming to you with a Putnam Exam problem from 2023. So this is the first one, which means it's on the easier side, but I thought I'd give it a shot. So what I'm about to do is walk you through how I would approach the problem, and I did check my answer to make sure it was correct, but other than that, everything that you see is all the problem solving that went through my head, so you can see it organically. Okay, so let's get to the problem. It says for a positive integer n, define f sub n of x as being the product of all these cosine functions, cosine x, cosine 2x, and so on until you get to cosine of nx. We are to find the smallest value of n such that the magnitude of the second derivative evaluated at 0 exceeds 2023. Okay, so before any of this, the first thing that I did was I took an arbitrary three functions, which I called f, g, and h, and I just took the derivative of it so I can kind of make sure that I had the symmetries correct. Okay, so in order to take the derivative of the product of more than two functions, you can use the product rule if you group it together like that. So then you essentially only have two functions. So the derivative is going to be the first times the derivative of the second plus the second times the derivative of the first. And then we do have to use the product rule again on these two functions. So that's going to be the first times the derivative of the second plus the second times the derivative of the first. So if you kind of look at this carefully, you'll notice that this is very symmetric, and essentially what it is it's the product of the functions f, g, and h copied down 3 times, where each time you distribute the one derivative, this one tick mark, in a different place each time. Okay, so maybe for the first term, it doesn't really matter where you put it, but I'll put it on the f for the first term, I'll put it on the g for the second term, and I'll put it on the h for the third term. As long as all three of them have one tick mark, then we're golden. Okay, so then how do we take the second derivative of this? Well, the second derivative is just the derivative of this, which means we essentially have to do the same thing. So for each of these three terms, the derivative of each of these is going to produce another 3 terms. So there's going to be a total of 9 terms, and it's not a coincidence that 9 is the number of functions to the second power. That's exactly what it's going to be. But in order to take the second derivative, we're just going to kind of do this term by term. So for the first 3 terms, what we're going to do is we're just going to copy down f prime g h 3 times. And you can work this out to make sure that this is correct. But then the second derivative is going to go in one of 3 places. So for the first term, we'll put that on f. Second term, we'll put it on g. Third term, we'll put it on h. Okay, so then we're going to do the same thing with these terms. I'm again going to copy down f g prime h 3 times. And as I do this, I want you to notice if there are any terms that start to repeat. Okay, so I'll put a tick mark on the f, tick mark on the g, tick mark on the h. Okay, and the last 3 terms, it's going to be from that product. So that's going to be plus, and now I'm going to copy down f, g, h prime, f, g, h prime, f, g, h prime. Put a prime here, prime there, a little bit of prime everywhere. Good thing we're not Amazon. All right, so the idea is I argue that there are actually 2 different kinds of terms. Okay, so there are 2 different kinds of terms. The first kind of term is one where one function has the second derivative and the other functions don't have any derivatives. Okay, so basically, first type of term is one with a single second derivative. And the second kind of term, since we're taking the second derivative, it doesn't matter how many functions I'm multiplying together. I could have 10 functions. And if I take the second derivative, 2 of the terms are each going to have a first derivative. Okay, so there's 2 first derivatives. Okay, And I argue that actually one of these terms is completely redundant for the purpose of this problem. Okay, but let's go ahead and look at what we're trying to do. So the product of terms in question is just a bunch of cosines. Okay, so the first type of term, this one where there's a second derivative, there are always going to be n of those terms. In this case, we had 3 of those terms, but that's because for each one of these, for each function, there is only one way that you can have a second derivative. But for the second type of term, it's a little more complicated, right? Because how many different ways can you have 2 first derivatives? Well, you can have a lot of different ways. So for example, f prime g prime h is the same as g prime f prime h. So a lot of these are actually double counted, and in fact, all the remaining terms are double counted. And since there's an even number, you can divide that by 2. It doesn't really matter, it's not really the purpose of the problem, but that was kind of a tangent that I went down. But in the end, let's take a look at these separately and just kind of play around with it for a little bit. Okay, so to get a feel for the different kinds of terms we have, let's go ahead and just take the first one, and I'll just give you an example of term number 1. Okay, so it's going to be something of the form, perhaps, it's going to be cosine of 1x times cosine of 2x. This is the first kind of term, yada yada, until maybe some cosine of kx, and I'm choosing this to be my second derivative, yada yada, all the way until cosine of nx. Okay, so this term I'm choosing to take the second derivative of, and then everything else is just the same. Okay? So, what is that going to amount to? Well, what's the derivative of cosine of kx? Well, if I have cosine of kx, and I differentiate once, that's going to be a negative k sine of kx. Where did the k come from? That came from the chain rule. Okay, and then if I differentiate a second time, I'm going to pick up another k. That's going to be k squared cosine kx. Okay, so the first term is going to essentially look like cosine of 1x, cosine of 2x, yada yada, cosine of kx, cosine of nx, times negative k squared. Okay, and what's term 2 going to look like? Well, term 2, I don't know, just pick any 2 of the cosines to take the derivative of. Again, I'm trying to be as clear as possible. So maybe cosine of x, yada yada, cosine of, I don't know, maybe some kx, maybe some cosine of mx, and then we get to cosine of nx finally. And I'm choosing, I'm choosing these 2 terms to just take a first derivative of. All right. Well, if I do that, then almost all the terms are going to stay the same, but then I'm going to have, this is going to be a negative sine of kx, and this is also going to be a negative sine, this time of mx. But then the chain rule that I applied twice, I'm going to pick up a negative k times a negative k, which is just a positive k squared. Okay, now, if you look up to the problem, all of those terms, and again, there are going to be n squared of those terms, and n could be 100. It doesn't really matter how big it is, but I'm just grouping them into 2 different kinds of terms. But you're going to have to take all of those terms, evaluate it at 0, and then take the magnitude. Okay? So what you're going to have to essentially do is plug in 0 and see what happens. Okay, so for terms of the first type, we have that, if you evaluate that at 0, let's see, cosine of 0, cosine of 2 times 0, yada yada, cosine of k times 0. All we have is cosines. And if you plug in a 0 everywhere you see an x, the only thing that you're going to pick up is 1s, right? That's a 1, that's a 1, etc. And then if I take the magnitude of this, I'm just going to pick up a k squared. Right? And of course, k is just some number between 1 and n, and in fact, it's all of them. Each of those n terms, you're going to have to do that for them and then sum them up. Okay? Now, for terms of the second type, you can already probably guess what's going to happen, but I'll just show you anyway. What you have is, you have what? Cosine of 0, sine of k times 0, and then who cares? Because sine of 0 is 0, which means this whole thing just evaluates to 0. It doesn't really matter what else I have. Therefore, I can exclude term 2, and I only care about things where each of the n functions has a second derivative, and all the rest are 1s. Okay, so what I'm going to have is that the magnitude of fn double prime evaluated at 0 is going to end up being, let's see, well, it's going to be, it's going to be a sum from k equals 1 to n of k squared, because that's what a typical element's going to look like. And what I need is that to exceed 2023. Okay. Now, how are we going to do that? Well, this is one of Gauss's formulas, right? And this is actually evaluated to be n times n plus 1 times 2n plus 1 all divided by 6. And we need that to exceed 2023. We want to find the smallest n that exceeds that. Okay? Now, if you didn't know that, if you didn't have that memorized, this is bounded below by n cubed. And, as an exercise, you should show that. So basically, you can just keep testing stuff until you get something that exceeds n cubed, where n cubed exceeds 2023. And then from there, you can just start decreasing n gradually and actually plugging it into the real formula until something works. It'll take an hour, but that works. Okay, I think this is the most straightforward way to do it, though. And there are a couple ways you could do this. The first way, I'm sure if you multiply everything out, you'll get a cubic equation, and some people are really good at solving cubic equations. I'm sure all the members of the Putnam exam can solve cubic equations. I'm still a little rusty on that. I don't have the cubic formula memorized or the Viette formulas memorized. So what I did is this. First step, multiply both sides by 6. Okay, so I get n times n plus 1 times 2n plus 1 needs to exceed 6 times 2023. Okay, the second thing I did was I actually just approximated this. Okay, so I approximated this because this is asymptotic to 2n cubed. And I need to find n so that 2n cubed exceeds 6 times 2023. The reason I did that was now I can go ahead and divide both sides by 2, and I get that this is equivalent to finding n so that n cubed exceeds 3 times 2023, or 69. So at this point, it's really just kind of plugging in until you find an n. And then note that this is actually greater than the 2n cubed. So if you find that magic n that exceeds this, then you start decreasing it and actually plugging it into the real equation until you get the right answer. At least that was my approach. So how do we find n so that n cubed is greater than 6069? Again, I'm sure people have clever solutions, and if you have one, go ahead and put it in the comments. But the way I did it was I just knew that 20 cubed was 8,000. It's a pretty easy cube. So I just decreased it and figured it out. So the next thing I did was I took 19 cubed, and again, I didn't use a calculator because I assume the people at the Putnam Exam don't have calculators. So how do we do that? Well, 19 is 10 plus 9. And then I used Pascal's triangle to figure out the coefficients. So remember, Pascal's triangle looks like this. Okay, this is, if the exponent here were 0, this would be the coefficient. The exponent were 1, 2, and then this bottom row is when the exponent is 3, which is what applies. Okay, so what that means is this is going to be, 10 cubed plus 3 times 10 squared times 9 to the first plus 3 times 10 to the first times 9 squared plus, I really should say this is a 1, plus 1 times 9 cubed. Right, so the Pascal's triangle, what that gave us were these coefficients. 1, 3, 3, 1. Okay, and these are pretty simple to do. 10 cubed is 1,000. 10 squared times 9 is 900, times 3 is 2,700. 9 squared is 81, times 3 is 243, add a 0. And then 9 cubed is 729, I think. Okay, and then I just added these together. Again, you just need to make sure whether or not it exceeds 6069. And then we get what? This is 3,800 plus, let's see, 3,159, which is, well, that is definitely going to exceed it, right? Okay, does that mean 19 is our answer? No. What it means is we have to check if 18 works. Okay. And it turns out that 18 isn't going to work for this one. So now we have to go back to this equation. We have to see if it works. Well, clearly, if this expression was bigger than the previous one, 19 is going to exceed that too. So let's check if 18 exceeds that. So what I have to check is I have to check if 18 times 18 plus 1 times 2 times 18 plus 1 all over 6. I have to check if that exceeds 2023. That's a good thing because 6 does go evenly into 18. So that's going to imply I have 3 here, 19 here, double 18 and add 1, that's 37. Okay, and I have to see if that exceeds 2023. Okay, and how are we going to do that? Well, 19 I wrote as 20 minus 1. Okay, so multiplying these, I got, let's see, that's going to get me 740 minus 37. Okay, which got me, what, 703. Okay, and then 703 times 3, that's 2109. And that does exceed 2023. Okay, which means n equals 18 works. I don't know if that's my answer or not. In order to check that, I would have to plug in n equals 17. I'm just going to go ahead and finish this problem off by saying that when I did that, if you go ahead and plug in n equals 17, the inequality is not true, which means that n equals 18 is the smallest value then that makes the second derivative evaluated as 0 work out. So n equals 18 is my answer.